Welcome back. Today we continue with the program of looking at the very first ideas of renormalization. So last video we did look at the mass renormalization, the field renormalization, and now we want to look at the vertex functions and the renormalization of couplings. Right? Of course, now we're pushing a little bit on this idea of trying to do things without specifying the theory, right? We have been restricting ourselves to scalar fields, but not so much to any particular interaction, right? Now you'll see that I'll keep doing that for a while, but eventually I'll have to start looking at a specific interaction. In our case here, it will be lambda phi 4 interaction. Right? But even that, so far, we'll try to just not do any specific calculations in lambda phi 4, but just look at the general ideas, and we finally get down to the specifics at the second order in perturbation theory on the next video. Right? So as we're pushing a little bit already, this subject is a little spread out in the references. So the first part of what we will discuss is in Peskin, in Schroeder, and in Ryder. And the second part, which is this renormalization of lambda phi 4, you can find in an introductory way, right? Not the full renormalization, but just the very first ideas you can find in Cheng and Lee and Schwartz. So what we're looking at right now, right, is the other part of this division that we did on the previous video, right? We decided to take the full connected green function of a 2-to-2 scattering and divide it into two parts, essentially, right? We have shown that you can separate these into full propagators for the external lines and something that we call the amputated green function that rests here in the middle and really has to do with the interaction. I cannot find any piece here that is just a contribution to this leg. Right? And we've shown that near the pole, these things behaves as a product of full propagators for these external legs. Again, keep in mind that I'm restricting myself to a scalar theory with just one field. There's just one particle here, one scalar, right? And also, while in the very first lectures in this series, I have been talking about composite states, that I could go near the pole of something that is a particle that is equivalent to a field in the Lagrangian, or to some bound states that arises from the interactions of these particles. Now I'm going towards the perturbative regime of these theories, and now I can really just worry, right? For a weak theory, I know there will be a free particle which is equivalent to one field in the Lagrangian, right? There's no complications like confinement, bound states, nothing like that. So now, while it is implicit that the mass I'm putting here is always the mass for that lowest lying state, which is a one particle equivalent to a field in the Lagrangian. Now that we know that that's not the only thing that can appear, we want to focus on it because it's the simplest case, right? And that's where we'll be able to learn a lot. So I have shown that near the pole for that, if all the four external lines are really producing that particle, and that's why I have the same mass everywhere here, I can write this full amputated green function in terms of the four complete propagators. So I have these field renormalization constants here, I have the physical masses down here. And of course, what is left is that kernel there, that term that contains the interaction. If I compare these with the LSZ reduction formula, I also know that these green functions should behave near the pole, right? Which is the same as up here, as these propagators, but now I have x to 1/2 here, so I have square root of z, actually, square root of z everywhere, times the matrix element, the S matrix element, right? P1, P2, S, K1, K2, right here. So if I compare these two, and I'm only looking at these most singular terms here and not the rest, right? I can get the conclusion that the S matrix element should be equal to this times a power of z, right? If I take all these z's and compare with the other side, you see I'm left with a z square here. So the importance of studying these core object here cannot be underestimated, because this is where the actual S matrix element is coming from, right? And the contribution for the full propagators is being carried through this field renormalization constant, right? But that, depending on how I define my fields in the Lagrangian, as I have already shown, I can get rid of the z square over here, right? I could do something very similar to this to more complicated green functions with a similar conclusion, right? So I could take 2 to n scattering, so I just increase the number of final states from P1 to Pn, right? N. And then I'll have something that looks like this, keeping the initial states, just K1 and K2. I don't need these arrows here anymore. Or here, by the way, these are just labels. And in this case, I'll have a square root of z for each particle, right? So in total are n plus 2 particles. And then I have an amputated diagram that goes here. So this is what I'm looking at for a more general case. Make this a little bit pretty. Because this is what I get from the LSZ reduction form. Now, what we want to do with these amputated green functions is very similar to what we did with the full propagators, right? In the case of the full propagators, we were able to show that in general, a full propagator, like anything here, could be written as a sum of the free propagator plus things that involved one pi contributions. Right? So I had a whole series that look like this. Let me just draw the very first terms. Right? I was able to write something like that. Now I want to do the same for the endpoint 1 pi contribution. So I want to define something that is intrinsically a 3-point green function that cannot be further divided. So for instance, this would be a 1 pi green function with 3 external legs. This is just a symbol, these external legs. And that's why I indicated them here with dashed lines. This is just a symbol saying that this is a function that depends on 3 input momenta or 3 positions. But for instance, if I think about this contribution here, this thing would include, for instance, in lambda phi 4, something like that, or even something like that. But it wouldn't if you have a theory, for instance, that allows something like this, 3 lines, gamma 3, gamma 3, another 2 lines, this is not in here, right? It's not contained in there because these can be separated into 2, 3 line contributions just by cutting one propagator, right? So it's not intrinsically a contribution to the 4 point vertex function. So these gamma n are the vertex functions I'm talking about, and they are the generalization of the 1pi diagrams that I defined for the 2-point function. So just to give some examples, right? We could go to lambda phi 4 theory, for instance, right? And define something that is the vertex function for lambda phi 4, right? Which is composed by this contribution, for instance, plus something that looks like this. This is the second order contribution, right? You can see that because it's already 2 vertices here, and we know that at this order there are other 2 contributions to this. There's this one, and also something which looks very ugly, which is this one, kind of the U channel of this one. Now this line goes here and this one goes there and higher, right? And for that case, we can define this function as I gamma. It depends on 3 of these 4 momentum, right? Because of momentum conservation, I don't really need all 4 momenta entering here. It will be a function of just 3 variables. And it looks something like that, right? All these constants in front of it are just conventional. In this case, I decided to put an I here, which means that my gamma for this theory will be an expansion in the coupling constant that starts with minus lambda 0 and goes on, right? And all of these defines this gamma 4 of lambda phi 4, right? Usually when I am within the context of this lambda phi 4 theory, I don't need to name this guy gamma 4 because it's the main vertex function I'm interested in, so I don't need to name it. But it is a gamma 4, right? It's intrinsically 4 momenta vertex function. Say another theory that we have seen before is QED, right? I could do the same for QED. And then it would look like this, right? You usually define it this way. I'm just following, I think Peskin defines it this way. Right? It's now a function of 2 momenta, because it's QED is a vertex with 3 particles. The most important one, right, is just a fermion, and photon, right? It has also a Lorentz structure to it, right? Because this at leading order is minus I E0 gamma mu. And I'm taking care now of writing coupling constants that come straight from the Lagrangian with a 0 index to remember. This is really the parameter in the Lagrangian. Right? And of course, this receives loop contributions, which we'll calculate later. Right? With this definition, then gamma mu of P line P, which is chosen in this case to be the momentum of the fermions, right? Going into the vertex, will go like this, and that's what defines the gamma, the vertex function for QED, which in this case is a 3 momentum vertex. And by conservation of momenta, I can write in terms of 2. And again, I have dashed lines here because the propagators for the photon and the fermions are really not included here. They are included in the full propagator part. In fact, I have defined these guys before in the Quantum Field Theory 1 course. So if you go back to video 25 of Quantum Field Theory 1, you'll find these guys being defined as the 1pi functions generated by the effective action. When I was defining the effective action, I found all these vertex functions. In fact, in that context, I also defined a 2-point vertex function, which I called pi2 over there, which was given by something like a sum of intrinsically 2-point diagrams, right? Including, for instance, something that could be a mass term for the theory or a counter term that we just found when we were doing the mass renormalization of the theory, plus diagrams that were, again, intrinsically depending on 2 points, right? Like, so lambda phi 4 could be something like that, right? Or in QED, it could be something like this, right? Just a loop with a fermion. Here is everything I'm putting in dash lines represents something that I'm separating from pi2. It goes together with the full propagator, but here I have a pi2 contribution, which is just a photon correction to the fermion. And you now recognize these 2-point vertex functions as the self-energy, right? In this case, self-energy in lambda phi 4, and in this case, the self-energy for QED, right? The electron self-energy, if this fermion is an electron, right? And these played an important role in the mass normalization, where for a scalar theory, I named it m square of p square, right? So these vertex functions are very important. And now let's take a look on how they behave, right? For that, I have to specify a theory. There's just no way around it. So we go to our favorite, most simple one, which is, again, lambda phi 4. So the Lagrangian I have in mind is this one, in Minkowski space. And the scattering, the 2-2 scattering S-matrix element will be given by this, which in the case of lambda phi 4, I can argue to be equal to just the gamma 4 function, which I called just gamma in this case, right? And the argument here is fairly simple, right? Since in lambda phi 4, if I think of any diagram that could be happening there, if I go down with 2 lines into something, I always have to come out with another 2 lines, right? In other words, I know that I cannot separate this amplitude in something there is a gamma 3 times another gamma 3 connected with some propagators, simply because gamma 3 is 0 in lambda phi 4. There's no odd green functions different from 0. So in this case, it's just really this 4-point amputated amplitude is really just gamma 4, right? Then this, if I take S, exchange it by 1 plus IT, which is the non-trivial part of the scattering matrix. And then I know that T is just 2 pi to the fourth, 2 pi to the fourth conservation of momenta times m, right? Then I can easily, and the same is appearing on the side, right? These amputated green functions also has a factor of 2 pi to the fourth, also has conservation of momenta. Everything is appearing on both sides. I can easily reduce this to Im is equal to I z square gamma, and this gamma is really this gamma 4 using the definition I gave up here, right? So I'm leaving a factor of I outside for the sum of this whole series of 1pi diagrams, right? And I can also write, as I have said before, this, because of conservation of momenta, I can really describe these, the full kinematics of these vertex just in terms of 3 variables. And I'll choose those to be the Mandelstam variables, S, T, and U, which I define in the very last or next to last video in Quantum Field Theory 1. So if you don't know what Mandelstam variables are, go back to those lectures and take a look. Right, so this is the equation I'm working with so far, which relates these 1pi for point vertex to an element of the scattering matrix, right, which I use to do calculation. Right? Now what I want to do is compare these, what kind of information I can have from this guy that is comparable with experiments, right? So at 3 level, things are pretty straightforward, right? So we know that Z, this field renormalization constant, is 1 at 3 levels, and then there are contributions that I will indicate like that, right, which are at least linear in the coupling constant lambda 0 here, right? But need to be one loop contributions, right? We have seen this these on the previous video, right? And then there are bigger, higher order contributions too. But we have seen that these, which we call delta Z, only appears at loop level. So at 3 levels, Z is just 1. And this guy, which I'll indicate, this gamma, which I'll indicate now like this, right? At first order in perturbation theory. So remember, this is keeping track at the leading order contribution right, is in the coupling constant. So this is the power of the coupling constant I expect. It is just minus lambda 0, which again I'm using the definitions I did up here. So in this case, things are really straightforward, right? Because we know how to calculate this 2 to 2 scattering, right? We know how to obtain a cross section, which is given, right? The differential cross section for a 2 to 2 scattering in this theory, right? This is the solid angle, is just this matrix element right here, square, over 64 pi square s square. S is the Mandelstam variable here, right? This is an energy, center of mass energy square. And at this order in perturbation theory, right? Since this guy is just minus lambda 0, right, by this equation right here, I just have to substitute everything up here. This is just lambda 0 square over 64 pi square pi square s square, right? I can disregard this contribution for z anyway, because when I multiply z by lambda, since lambda is already order lambda gamma, since gamma is already order lambda 0, any contribution that comes from z will be higher order in the expansion of lambda 0 in this multiplication. Right? So what I'm looking at here is that arguably I can do an experiment, right? Of course, the experiment will be done at a particular energy with a particular combination of momenta, right? I measure the particles coming out, but all of that, every measurement I do on this, I can map to a point with a particular s, t, and u, which depend on the momenta of the incoming and outgoing particles, but I know how to calculate that, right? And at that point, I can see what's the chance of scattering at a particular combination and measure this quantity, right, for a small solid angle. That means that from here, I obtain, just using this equation for the value of s that I got here, right, I have this, right, and then directly I can map these to a value of gamma 0. So if this was the whole story, right, I could in principle say, well, lambda 0 is a physical observable quantity in a slightly indirect way, but that's good enough for most of our quantities, right? But of course, things get a lot more complicated either if I go to the next to leading order calculation, because now I have to use more, I have to go further in these expansions, right? So I could add here for gamma. Now I'll write gamma as gamma at first order in perturbation, that plus gamma at second order, plus higher powers of lambda 0. And that means that now the matrix element will be equal, again, I z squared, which itself has an expansion on powers of lambda 0 times these ones, right? Plus whatever, right? The higher order contribution. Now I can rewrite this using the expressions above as this one is just minus lambda 0. I'll put the I inside, so this will be minus I lambda 0. And this guy, I'll put the I here. Right? But I know what kind of shape this guy has, right? Is a function of st and u in general. I don't want right now to calculate, right? But let's keep in mind that I'm pretty sure this guy will come from those 3 diagrams I draw up here, right? These 3 diagrams I drew up here, right? Which means this guy is proportional to the coupling constant square. Right? This will not be very important for us right now, but I just want to mention that this guy is something like minus I lambda 0 square and some function of s, t, and u. That can be very complicated. I would have to really do the loop calculation. The important point here is that this is order lambda 0 square, right? That's the part I'm trying to convey with this number 2 right here, right? So this is an important equation I obtain here, which I'll use a lot. Let me move it apart here. Prettify it. Right? So this is true. I'm getting rid of the higher orders here. This is true at second order in perturbation theory, right? Of course, I still have to expand Z in order to know there are more things I can throw away here inside the Z, right? But I won't need to do that right now. The important part here is that this argument that I use here, right, this flow of information is now disrupted, right? This part is okay. It is true that I can still measure cross sections, right? Still true that for each of these measurements I can assign a value of ST and U, right? And that allows me to use the same formula I used before to obtain a value for M, right? But now I have to plug in, if I want to go further than this, I have to plug in this equation right here. I have to solve it. So know this function f STU that will allow me to put a lambda 0 here times this, and then I have to solve this for lambda 0, right? Which means that the lambda 0 I obtain right now it will be necessarily a function of S, T, and U. Unless that function f up here is really simple, so it's just a constant, right? Which we know is not the case, right? So things get complicated. That's the message, right? Now I have a quantity which is more loosely connected to what I wanted the coupling constant to be, right? You want a coupling constant to be this number that gives you the intrinsic strength of the interaction in your theory. And now this lambda 0 is dependent on not only on the energy and combination of momentum you used to measure, but also in how far you went with this expansion, right? Which is getting dirty. And it can get worse, right? Because now, let's think what happens if this guy is a divergent quantity, right? It's infinity, right? Then I have to do something, right? I'll have to do some procedure here to separate physical information here, because of course, this needs to be finite, this is finite, right? And I have to separate the physical information here, which will necessarily, as we shall see in the rest of the course, implies new parameters, usually new scales, which parameterize your ignorance, right? We'll get to that. Right now it's just empty words, but that will demand of us to limit the validity of our theory. Typically those things will blow up because I'm doing integrals to arbitrarily large energies, right? And I'll say, well, my theory is not really valid up to those energies, so it will be valid up to some new scale, lambda, right? And this becomes a parameter in my theory. But if that parameter is here, that means it will be here. Now, if I do a measurement, get a matrix element, and want to compare it to some lambda 0, and I regularized these divergent loops here, right? My answer for what lambda 0 is will also depend on these new scales, which is even more awkward because now these new parameters or new scales are really far away from the scales I'm measuring, making my measurement in, right? And that's a problem for physics, right? If you need to describe a system, and the system is dependent on scales of size or energy, which are very different from the scale you are working with, you don't have a separation of scales that can make your theory predictable, right? Just try to think what would happen if, in order to predict movement of, I don't know, billiard balls, you needed to worry about the movement of Saturn or the atoms inside the billiard balls, right? So these separation of scales are very important to produce theories which are useful, right? And we want quantum field theories to be useful. We know the results of quantum field theories match experiment. So this separation of scale needs to happen here somehow, right? And so the conclusion is that my measurements cannot be dependent on this unknown scale, right? I don't even know what is the energy where my theory or scale of size in which my theory loses its validity, right? So I want to define something else which is more useful and physical, right? All of these argument is showing that lambda 0 is not really the physical coupling constant, that thing that characterizes the strength of my interaction at the scale I'm doing my measurements. So let me do something else, right? Which is pretty straightforward, right? I'll just choose a particular point in this kinematic variable space. So let's choose a particular value of S0, of ST and U, which I'll call S0, T0, and U0. Can be anything, as long as is in the region where I can do measurements, so it roughly in the scale I want to describe, right? And let's define the coupling constant as the value. So define I lambda. So now I'm defining this lambda, which is different from lambda 0, by the measurement of m I did at that reference point, right? You can think of this as a reference frame in which these two quantities are equal. And of course, this equality is again the same way we did for the physical, for Z and the physical mass, right? This is inspired by how the tree-level theory behaves, right? So we know that at tree-level, I went too far, this is true. And I'm imposing the same now at this particular scale, right? Because I cannot avoid the fact that now if this guy changes for different ST and U, that means I'll have to choose a particular reference point, right? Writing this explicitly, what I'm saying is that this new physical coupling constant will be given in terms of Z squared minus I lambda 0 plus I gamma 2 of, and this of course is a function of lambda 0 because when I calculate the loops, I already know this will be proportional to lambda 0 square. Also S0, T0, U0, and possible new parameters if this was divergent at all. Again, I want to convey the message that you could and would probably want to do this even if you were talking about finite quantum field theories. But we know, right, that's information that probably people already gave spoilers to you, that quantum field theory has divergences on these loops. So I'll not pretend you don't know that, right? Then, using this definition, right, I can isolate lambda here, just write it more explicitly without so many factors of I and such as this. Right? So this is important, something to keep in mind. And of course, the same as I did before, this allows me also to do a definition of something that I'll call delta lambda, which in this case, I'll just write in terms of lambda 0 z squared, right? Of course, motivated by this, minus lambda. So at this order, right, this is an equation that is only valid at order lambda 0 squared, in the expansion of lambda 0. But this is more general. I wanted this definition to be used even at higher orders, which means that delta lambda will be gamma 2 plus higher order terms. Right? So I'll keep this definition even when I go beyond leading order in the contributions for delta lambda, right? The very first contribution to delta lambda is at order 2 in lambda 0, right? Which again reinforces the same interpretation for everything else, right? That delta lambda really only appears at loop level, right? We know this guy contains loops, right? So now this is clearly defined, right? So this lambda, of course, is defined at this point in the this reference point in the space of possible scatterings, right? But also you can conclude from this that if I want to know now, let's suppose I want to know m at some other point, let's call this S1, T1, U1, right? This is also an observable quantity. In principle, I can just set up my experiment to measure these matrix elements at a different combination of S, T, and U, right? Since this is a physical measurement, and this is a physical measurement, both need to be finite, and so the difference between them needs also to be finite. So this will be some function of the physical coupling constant, S1, which is a finite well-known quantity, right? And these new variables, right? And here you could argue that S0, T0, and U0 should be here too, but they are implicit in the definition of this guy. Right? And that means that the theory I'm now building not only tells me how to measure a physically meaningful coupling constant, this renormalized coupling constant, but also tells me that the theory, if I calculate the loops, right, and make this difference, right, I can predict what if I know how to calculate this G, I'll be able to predict measurements in points away from that reference point I choose at the start, right? How far away is a good question, right? We'll have to actually do calculations to discuss how far away can I go from this reference point, and what means close or far from this reference point. In what sense I'm close or far from it, right? But we'll get to that later, right? For now, what I can do is the same I did in the case of the mass and the field renormalization. I can go back with this definition, right, to the Lagrangian and see what happened, right? What happened. So before we did write the Lagrangian, which before any redefinition of fields looked like this, and using the following definition, so I use z equal 1 plus delta z. I use that phi renormalized is equal to the z minus half phi, and I use that the physical mass is m0 square z minus delta m square. I was able to rewrite this Lagrangian using those three definitions in this way, right? This became half of del mu phi renormalized, del mu phi renormalized minus physical mass square phi renormalized square plus an interacting piece which was comprised of delta z over 2 del mu phi renormalized, del mu phi renormalized minus delta m square over 2 phi r square minus the renormalization of the interaction, right? The potential. And now this is the part I'm interested in, right? Before I just avoided discussing it. Now I can do it, right? So in our case here, since we're dealing with lambda phi 4, v of phi is just lambda 0 over 4 factorial times phi to the fourth, right? And now by using this renormalization of the field, right, I can write VR of phi r like z square times phi r to the fourth, right? Which now I can substitute, right? The z square lambda 0 can be substituted using this definition I have up here, right? Which works pretty well because now this is just the renormalized coupling phi r to the fourth plus delta lambda phi to the fourth, right? Which now I know how to get Feynman rules from, right? This is just the same as lambda phi 4, right? And I have a new lambda phi 4 like interaction, which is a new counter term, right? This plays a role which is very similar to this one and this one. This is again what we call a counter term. And here are the two new Feynman rules, right? One is just the usual phi 4 vertex, but now instead of having lambda 0, I have the physical coupling. And this new counter term, again, I'm indicating counter terms by these crossed out vertex here. So now with these new variables, right, the Lagrangian written in terms of these new variables, I can calculate my vertex function. I'll just call this the renormalized vertex function. And it will be just this vertex, this contribution. But remember now that I'm just writing, this is just really the vertex. There's nothing for the propagators here, plus this one, and since this guy, I'm already showing that this guy is only appearing at order lambda 0 square. I also need to do a consistent expansion to include other diagrams that appear at lambda 0 square expansion, right? Like this one, this one. This is the three guys that will be pretty soon calculating. And I keep the same mistake. This one. And of course there's more, right? If you go to higher orders. Yes, this vertex is the same as this one, right? So there's one here, 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 here. And again, by every diagram here, I really mean just the internal contribution and not the propagators outside, because I'm talking about the vertex function. This, of course, can be written using the rules upstairs, minus I lambda, minus I delta lambda, plus, and again, the sum of these three guys I called I gamma second order, right? And now renormalize. Renormalize just to remember which rules are we using for the propagators, for instance, right? Which at these, with these variables have no z, for instance, plus the rest of the perturbative expansion. Which means that if I want to calculate a matrix element for in terms of these variables, right? IM will be just I gamma R, S, T, and U. So there's no z squared anymore here, because in the renormalized or the renormalized field, the propagators don't have the z square, right? And this is this expansion up to second order in perturbation, right? Theory. And of course, now to give some meaning for this delta lambda, which is defined here, I need a renormalization condition, right? Which again is implicit in the whole calculation. Now I want to make it explicit, right? And I defined it as a measurement of this for a particular reference point, which using this equation I can write in this way. So now I'm writing an equation for lambda, which is valid at this specific point in this STU space, this reference point, right? And this is the physical definition I did before, right? Of course, now I can go back up here, right, using this at second order in perturbation theory, and rewrite this equation as, right, on this side, I just eliminate all the i's there, and I can write this guy as just minus lambda, and the right side of this equation will be just minus lambda minus delta lambda, and this calculated at this point, right, plus S0, T0, U0, which implies, of course, that delta lambda is equal to that vertex function calculated at the reference point. And here you might be, reminding yourself of what happened in the mass and renormalization, right? Which is the same. So if this guy here is dependent on ST and U and has very complicated dependence, right? At this point, S0, T0, U0, even it could be dependent on these new scales that come with trying to eliminate the divergences, right? These dependencies all need to be concealed with whatever is coming from the counter term. So there's a cancellation between these two guys as to keep the renormalization condition at the reference point. That happened for the mass too, right? I also choose to define the mass at a reference point. The thing is, there I had a natural, let's say, reference point, which is the position of the pole, right? Here I have more freedom, right? And so I just choose anything, right? In fact, that cancellation, you could always have guessed it from the equation where I first define lambda, right? When I do this definition right here, right, I'm saying this is a measurement, right, which I'm relating straight away to lambda. So I don't need anything on this side of the equation to really know lambda. I measure this and I know how much, what the value for lambda, which means that everything that is happening here needs to happen in a way that spurious dependencies, so all these variables here, need to disappear by redefining lambda 0. Lambda 0 will be whatever I want because it's completely irrelevant for the measurement, which is defined here, right? So whatever the value lambda 0 assumes, it will depend on what choice I made for these parameters. So there's a cancellation here that eliminates unphysical dependencies, and with those also the divergences. And that defines a physical constant. So as a final comment I want to make before finishing this video, also here we can see what happens if I want to calculate M or compare with experiment for the matrix element at different points in the STU space. So I can use this equation to rewrite M of STU as lambda plus these. Of course, this equation is only valid up to this order in perturbation theory. There will be other contributions for higher orders. But at this order, this guy is just this. S0, T0, U0, right? This is a finite quantity, this one too. That means if there are divergences here, they need to cancel between these two terms. They both will contain the divergences, right? And what I did here is just replace delta lambda by this expression here, right? Which means that if I compare two different points, let's call this one S2, T2, U2 minus the matrix element at another point, let's call this one S1, T1, U1, right? I just have to subtract two expressions like this and get this minus one minus this one, right? Which is a very beautiful thing, because now, for one, I can argue that this needs to be finite because it's two possible measurements. That means any divergences here need to cancel out. But also in this case, you see that even the reference point is not that important, right? I can by knowing the measurement at any point in parameter space, I can predict, if I know how to calculate these within my theory, I can predict values for measurements away from that point. And again, how far away I can go, we will analyze later. But even the reference point, you can see here, it's not that important, right? It goes away, and the infinities need to go away too. So that's the message for today. And keep in mind, what we're seeing here is that this guy, that's one prediction. Once you put loops in the theory, the matrix element itself will change with momentum, right? energy in most cases, but let's keep it general for now, right? Will change with these variables. And that's a change besides that which is in the Lagrangian. For instance, you could think of theories that have, I don't know, derivative couplings in the Lagrangian, right? Something like that, for instance. There's a derivative here, so this vertex depends on momentum, right? That's a possible dependency for the Feynman rule for this theory, but this is new. This is new because in this theory, there was no momentum dependence in the Lagrangian. This is something that is changing with the scale of the theory, which is being generated by loops. And that's an important prediction and will have very important consequences for these field theories, which we'll analyze once we start doing the calculations, right? Which now we cannot avoid anymore. So starting next video, we'll start calculating loops and dedicating our time, a lot of our time, to learn techniques on how to calculate loops and how to parameterize these divergences that appear in 4 space-time dimensions. Okay? See you then.